Welcome, dear viewers, to our video on momentum and impulse, two very important parts of physics. So, do you remember from the last video when we were talking about Newton's second law of motion, our favorite law of motion, or the net force equals mass multiplied by acceleration? Yes, remember that? Well, how did we even get there? How did we determine the relationship between mass and acceleration and net force? Well, we know from Newton's first law that acceleration is simply an unbalanced force acting upon an object that causes it to change its movement. So what are the two factors that would indeed affect that? Well, first, you're changing the movement itself. So velocity is one of those. And if you have a bigger object, it's obviously going to be tougher to change it, so Mass and velocity are the two factors that change this relationship. So, as physicists, we had to find the relationship between the two of them, didn't we? Yes, we did. And that gives you momentum, or P. And P equals mass times velocity. Wow. And what's the units for that, you ask? Well, it's got a really fancy name. It's kilograms times meters per second. Yeah, it's really long and unwieldy, and nobody came up with a better name for it, so we're stuck with it. Also, momentum is a vector, so you must always account direction in it when you are doing momentum calculations. And thusly, that gives you basically what momentum is. But momentum on its own is pretty useless to us unless we also take into account impulse. And what is impulse, you ask? And impulse is very simply the change in momentum. The change in momentum is what we're interested in because that is what changes our acceleration and therefore gives us Newton's second law. So change in momentum is just going to be mv final minus mv initial. There's your impulse. And so let's take an example of finding impulse. Let's say you have a ball that you threw at a wall and another ball that you also threw at the wall. Balls 1 and 2. And here's your wall. Let's say when you threw the first ball, it had a certain velocity. And when you threw the second ball, it also had a certain velocity. They're not equal. And then in a moment afterwards, first ball, ball 1, bounced off the wall and now has an equal velocity to its initial, but in the opposite direction. And the second ball just kind of stopped and got stuck to the wall. Well, find the impulse for each of those. You get m times negative v, so negative mv for ball 1, and then you subtract it from your initial, which would be positive mv, which ends up equaling negative 2 mv. And then for the second one, well, what's your final? Your final was just 0, and your initial was mv, and you get negative mv. Bam! It's very simple to find your impulse, and but what's important about it is how it relates to force. So, let's take a quick equation here. Let's take our equation of impulse. We've got mv final minus mv initial. Let's find the rate of change of that. What's the rate of change? How do we find that? Well, we put it over time. Change in time to be specific. Now let's simplify that. Let's make it equal to mass times v final minus v initial over change in time. Now, what is v final minus v initial over change in time, might I ask? Acceleration, did you say? You'd be correct. So we can equate that to mass times acceleration. And what is that equal to? Force. So now you can very safely say that your force equals your mass times your acceleration. Bam, bam, super simple. It's really a very simple concept, and it basically helps us. It basically is telling us that changes in mass and velocity result in changes in acceleration, which results therefore in a change of force, which is really the point that they're trying to get across here. And so now that we've covered that, Newton's whole second law bonanza, well, he had 3 of them. If you remember, there are 3 of Newton's laws, and the third one is quite simple. And the third law of motion is, as you may have heard it, every reaction has an equal and opposite reaction. which is really confusing because it doesn't really simplify that into anything. So we're going to simplify it. So if body A, we'll say, exerts a force on body B, body B will exert a force of equal magnitude but opposite direction on body A. And what's an example of that? And a really simple example is the Earth. Hey, look, it's the Earth. And a person. Look, it's a little stick figure person. Well, the Earth is always exerting a force on you. It's called the force of gravity. Force of gravity going down. And there is an equal and opposite reaction of force that you are exerting on the Earth, which is the normal force, which goes up. They're equal and opposite, and therefore you can stand on the Earth without rocketing to the very center or flying up into space. And that is a very simple example of that. There's always an equal and opposite force. Let's see. For example, let's say I have another stick person trying to push his car. We don't know why he's trying to push his car, we just know he's trying to do it. Well, he's exerting an applied force on that car. But the car is also exerting a normal force back on him that is of equal and opposite magnitude. Why can the car move then, you may be asking? Well, that's because it can roll. It's got the friction, which is also assisting in pushing it forward. And that's basically Newton's third law. And using that, there are a lot of interesting things that we can do. First of which, it just tells us that every action has an equal and opposite reaction, which allows us to derive a fundamental concept of physics, which is the law of conservation of momentum. That's right, momentum's back. We're talking about it again. And so we're going to talk about collisions. So let's say you have a ball, red ball, ball R, moving in a direction. It's moving a bit faster than blue ball, ball B. And then they collide. Shablamo. After that collision, they're both moving. It's just ball B is moving a bit faster now, and ball R is moving a bit slower. And so, let's apply Newton's three laws to see what we can learn from this situation. Well, the first law, it simply tells us that there was a collision. The blue ball sped up, it's moving faster, and the red ball slowed down, it's moving slower. Let's apply Newton's second law of that. Well, the second law says that our net force equals our mass times acceleration. It also equals the rate of change of our momentum, so our impulse over time. And so now we know that our force for the red ball, we're going to call that force 1 equals that. And our force for the blue ball also equals said principle. And now we apply Newton's third law, and that's where things get really interesting. You know that the red ball exerts a force here on the blue ball. But the blue ball, according to Newton's third law, is going to have to exert an equal and opposite force on the red ball. Meaning that force 1 of the red ball is going to equal force 2 of the blue ball. They're simply going to be opposites. And therefore, you can now equate these change in momentum equations. You can say that mvf minus mvi over t equals negative mvf minus mvi over t. And then you can simplify that into your mvi of body 1 plus your mvi of body 2 equals your mvf of body 1 plus your mvf of body 2, which is the law of conservation of momentum. And this fancy equation simply states that momentum is always conserved in closed systems. So as long as the system is closed and the forces are only caused and acted upon the bodies that you have in your system, momentum will be conserved. It will be the same when you start and when you finish. And that is very, very useful when we're talking about physics, because it helps us determine a myriad of things that you might want to discover. It helps you determine acceleration. It helps you determine force. As long as you know that momentum is the same, you can equate the forces at the beginning and the end. You can equate the momentum at the beginning of the end. And you can make your impulse, your change in momentum, equal 0. And so that's really an example. So let's talk about an example of that. Let's say we've got another collision. We've got a 100-gram red ball moving at 6 meters per second in this direction. And here we have a 500-gram ball just kind of sitting there. Afterwards, when they collide, they combine. They just kind of stick like Velcro. And they keep on moving in the same direction at a velocity v. Well, how do we find v, you may be asking? Well, we simply use the law of conservation of momentum. We take the momentum of the entire system before and equate it to the momentum of the entire system afterwards. And so, we take the mass, 100 grams, which is going to simplify very quickly. Remember, you always have to use SI units into 0.1 kilograms multiplied by 6 meters per second, plus our initial momentum of u is 0, you don't have a velocity, equals our final momentum, which, because these are combined, it's going to be their combined masses, or 0.6 multiplied by their combined final velocity. So then you simply take this equation, you divide both sides by 0.6, and you end up getting that your final velocity equals 1 meter per second. Shaboom, bam, boom. It's a very simple concept that allows you to find many things. And the same thing would apply for an explosion. What is an explosion, you ask? Well, it's the same as collision. Collisions are when two things collide. Explosions are when two things burst apart. And because both collisions and explosions are defined as closed systems, you can always count on momentum always being conserved in any collision or explosion that you may ever come across, which, once again, is a very useful concept. And so now we've got one more thing to talk about, and that's equating momentum and force. Now we'd just be sort of dealing in conservation of momentum, but if you put your force equation back up, your net force, and we'll take away the acceleration in this case and just make it your change in momentum over the change in time. If you rearrange that, you get your change in momentum equals force multiplied by change in time. And what's so special about that? You know your change in momentum, you remember what that is? It's impulse. Impulse equals force times change in time. But what's so special in that? And what's so special about that is that it gives us a linear relationship. This is your y, this is your m, and this is your x. So if you were to graph change in momentum, impulse, over change in time, force would be your slope. Oh my gosh. Yes, I know, it's very special. And so this helps us with adding time into our equations. And so now if you want to analyze a collision over time, say you have a ball that is colliding with a wall. You want to analyze the momentum at the moment that the ball is approaching the wall, at the moment that it's colliding, and at the moment it goes away. Well, this equation right here is very useful for determining the force that the ball is enacting on the wall and that the wall is enacting on the ball during that collision. Because during a momentum problem, you want to divide it into these three parts. Momentum will be something here. This is a moment where momentum will be conserved. This is a moment where momentum will be conserved. And this is also a moment where momentum will be conserved. But the velocities will be different in each of these moments, and that's why you split them into three separate problems. And so that really covers all that you can cover with momentum and impulse except for one more thing, which is pressure. And pressure is force over area. Wow! And we won't really be using pressure much in this unit, but it will come into useful later. So just know for now that a pressure is basically saying if your force is more spread out, it's not going to exert as much force in a certain amount of area. The unit is newtons times meters to the -2, also known as pascals. And with that, I bid you adieu. Meet me in the next video for work, energy, and power.